Now we will discuss how to find the limits of the function f of x at the positive infinity when f of x is a ratio of g of x and h of x, when g of x and h of x are not necessary polynomial functions. So in order to do this kind of problems, we want to compare the growing pace of each of the function g of x and h of x. So here's some examples on see how fast a function grows as x goes to infinity. We start with sine of x and cosine of x. Sine of x and cosine of x these functions grow at some intervals and decrease in some intervals, right? And regardless how far you go, it's always bounds between the two values. The range is bounded. And if you have a constant functions, it never grows. So then these functions grow slower than natural log of x. And natural log of x grows slower than polynomial functions except constants, right? And polynomial functions grows slower than exponential functions. So you can see that in this spectrum, exponential functions is the fastest growing functions compared to most other functions. So in the first case, we want to look at the first case, case number 1. The limit of the function f of x will be equal to 0 when x goes to infinity when the function h of x grows faster than the g of x. That means at x goes to infinity, the value of h of x will be much, much larger than the value of g of x. An example of this case is the limits of sine of x over natural log of x when x goes to infinity is 0. You see that sine is bounded between the two values, but natural log of x is slowly grows, but still growing. And another example is the limit of 2x over e to the x when x goes to infinity is 0. Again, e to the x grows pretty fast, much faster than 2 to the x, so the limit should be 0. In the second case is the limit of the function f of x will be equals to, be infinite limits if the function g of x grows faster than the function h of x. An example of this case is you have limit of 2 e to the x divided by x squared. So e to the x grows much, much faster compared to x squared. So the limits when x goes to 0 should be positive infinity in this case. And another example is the limit of x squared divided by natural log of x when x goes to infinity. And again, x squared grows faster than natural log of x, so we have the result at infinity as a limit. In the third case, you have the limit of this function f of x is constant at infinity if the leading terms of g of x and h of x are equivalent, right, or probably the same. And the limit will be the ratio of the leading coefficients. An example of this case is you have the limit of 2 e to the x plus 2x divided by negative 3 e to the x minus natural log x. If you look at the numerator, the leading term, the dominant term is e to the x because, again, e to the x grows faster than 2x. And similarly, the leading term is in the denominator is also e to the x because it grows faster than natural log of x. So then in this case, we want to look at just the ratio of the leading terms, right? The leading term can be cancelled out, and then the ratio of the coefficients is negative 2 over 3. Now, if you look at the second example, you have radical functions on the top and radical function at the bottom. But if you look at these two radical functions, they both have the same power, which is the leading power is 3 over 2 x cubed in the radical in the square root, right? So then if you look at just their leading terms, you can cancel the terms and you get the limit equals to the ratio of the leading coefficients, which is square root of 2 divided by negative square root of 3. So this is an general ideas on how to find limits at the positive infinity of a function f of x in this case.